Hello class, we are going to work on general like terms practice. It's not really from a certain section in your book, but it is very integral in a lot of the concepts that we will be working on. So let's get started. First of all, I'd like you to think in units that you know. So if we had the unit of 5 inches and we were trying to add 3 feet, we know that we'd have to do some conversion. We can't just add 5 plus 3 in different units to get to 8 something. We have to convert everything to inches, or we have to convert everything to feet. So since this can't be done without conversion, and we can't just add individual units that are not like in term, then we know that from our previous studies and experience that we have to do some work before we just add 5 and 3 together. So it is with like terms. Let's look. Say we had 5x plus 3 plus 4x. Three is like the unit of ones in the ones place for place value, and it does not match the other two terms that have an x attached to the whole number. So 3 is a constant term existing from just one whole number, but 5x and 4x are different kinds of terms with a different unit, x to the first power. Remember our invisible math, and that when an exponent isn't shown, it's to the first power. We just don't write it down every single time we write a number or a term in this instance, but we know it's there. So if all of this is true, is 3 a term just like 5x and 4x? No. So since that is true, what can we add in this example? The like terms in this example are 5x plus 4x. 3 is a separate type of term from 5x plus 4x. Since 5x and 4x have exactly the same types of elements, a whole number and x to the power of 1, we can add those together. And what is 5 plus 4? That would equal 9, and we repeat the x to add that like term. 3 added to 9x stays constant. We can't just add 9 and 3 here. They are not like terms. So we would have 5x plus 3 plus 4x. We would match our like terms. We'd say, okay, 5x plus 4x, that gets rid of those. The constant is the only thing left, and that is our final solution without having more information as to what x equals. Let's try another one. Let's think about 2x plus 5 minus x. So, in invisible math, we need to think there's a 1 in front of this x. We just don't write it down. So we need to look at 2x minus x as like terms. Even though there's not a 1 there, they are like terms. Plus 5. We can kind of put them together, group them together if you need to. What is 2 minus 1 in the like terms? 2x minus 1x. 2 minus 1 is 1, so it just leaves x. There is an invisible x in front of it. 5 is a constant term, and it cannot be added to an x term. 5. Okay, when you get more comfortable with like terms, your final solution would look like this without the invisible 1 in front of the x. Let's practice another one. This time, let's look at a squared term. So we have 3x squared plus 2x minus 5 plus 7x. That should be a plus. All right, look through here. Can you find two like terms that have different units, so to speak, than the other two terms that are available in our problem? The only two terms that are alike with exactly the same elements are 2x and 7x. 3x squared has a squared exponent. It's like a different kind of unit than x to the first power or 5 as a constant term. We can't just go through and add all of these together. We have to look for our like terms. So 3x squared doesn't have anything in this problem that matches it. It stays by itself. It stays the same. We've addressed this term. Now let's look. The only like terms that are in this problem are 2x plus 7x. So we say, okay, we can add these. 2 plus 7 is 9 with the same unit behind it, x. Plus 9x. We've addressed these. Now, the only term left is a negative 5, and it has no other like terms, so we subtract 5, and this is our final solution because there is no information for what x is, and this is as far as we can simplify this problem. Let's look at one or two more examples just to practice. We're going to change our variable. What if we have 7x plus 3y minus 4x plus 1? Let's look for like terms that have the same unit behind the whole number. X to the first power, x to the first power. Those are the same with the constants attached to these two terms. So 7x minus 4x is a like term. This is a y term. That's not an x term at all. So it sits by itself. There's nothing else that matches it. This is a constant term. It sits by itself. Nothing else matches it. So we're looking for what matches. So looking at our problem again, as it sits, we're going to address all the like terms that we can. So we'll have 7x minus 4x. They have the exact same elements in them, the same units of measure, so to speak. So 7 minus 4 is 3, and we attach the x to it just like it looks in those terms, with the exact same unit behind that 3. We've addressed these. The only thing left is a 3y by itself. Okay, we've addressed that one. It doesn't look like any other term in our problem. And then there's a constant by itself. Now we've simplified this problem as far as we can with the information we have. Okay, let's look at distributive property with like terms. So we have a problem that includes thinking about distributive property. And what's going to emerge from solving this problem and solving 4x from the distributive property is using like terms. Let's look at how to simplify this further. We know the information. We've used distributive property before. We're thinking about like terms, and we've solved for x before. We're just putting all of these ideas that we already have experience with together. So let's simplify the parentheses set with the distributive property. 2 times 4x. 2 times 4 is 8. The x labels that 8 because it's part of this element. 2 times 3 is a positive 3, so 2 times positive 3 is 6. We've addressed our parentheses set, just like you would in GEMS or PEMDAS. Okay, we still have minus x kind of hanging out there, and we transfer everything else down, equals 20. Okay, now we have a problem like we just saw earlier. What if we work with the like terms on this side of the equal sign? Remember the invisible 1 in front of a negative x, we just don't write it. Invisible math. What is 8x minus x? 7x. So we write 7x. We've addressed these. Plus 6 equals 20. We're going to go ahead and start solving. Minus 6, minus 6. So we're going to have, I'm going to take this up here just for the sake of room, 7x. Okay, address this. 6 minus 6, it goes away, equals, I address this. What's 20 minus 6? 14. Okay, now we can solve for x very easily by dividing by 7 on both sides. Keep equivalency on each side of the equal sign by doing the same operation on each side of the equal sign. This goes away because it's like 1 times x. In the identity property of multiplication, that says x is by itself now. And remember, the fraction bar is a division symbol. 14 divided by 7. We solved for x. If you wanted to check this, you would actually plug x equals 2. 2 in for everywhere you see x in the original problem. For a check to see if your answer is correct. Our answer is correct. And I hope this helps you think about using like terms, adding them together only if they are like units, and then using the distributive property to identify a problem where you can combine like terms and actually solve for x. I'll see you soon.